Well, welcome everybody. How's it going? Good? All right. So today we're going to spend some time studying structural mechanics in context of what we've done prior, mechanics of materials and design mechanical components, with now the opportunity to simulate these phenomena in ANSYS. Okay. So administratively, there is a convergence checkpoint due Friday, okay? And it's been great to talk to teams about what you're pursuing. I'm learning things as I've read your preliminary outlines. I'm learning things as I see your approaches, and it looks like we're going to have a nice group of projects. Please keep in mind that for convergence, what we're looking for is something related to mesh, something related to time, and something related to geometry. Okay? It's not 100% necessary that you do all three of these. Okay? Nonetheless, we want to see that we can get hopefully to a stable result. Okay? Some parameter of interest. Ideally, this parameter of interest would be connected to the hypothesis or hypotheses that you're testing. Okay? As people come in and talk about their projects, it's clear that we're very focused on getting the complexity, or capturing the complexity, capturing fidelity of the physical system. We really do want to emphasize that we're focused more on cause and effect relationships and being able to test hypotheses. So the key word there is something depends on something. Okay? So lift depends on the angle of attack. All right, well that may be almost a throwaway hypothesis in some cases, okay? Or the temperature, the temperature will depend on surface area. Okay, something like that. But we want to guide the simulations so you're not just doing random simulations, because there's not a whole lot of time either. Okay, if that makes sense. But guide the simulations that you choose to run based on the hypotheses that you're attempting to test. Okay? And if you have questions on what might be an effective hypothesis, please feel free to send me a message in Canvas inbox or come to office hours, right? I can't necessarily answer, a whole long set of emails from everybody on top of everything else we already have going on. I won't get to. But if you're concerned about your hypothesis, please contact me somehow, okay? The other thing I'd like to emphasize quite a bit with respect to the final projects is citations, or is the appropriate citation, or the appropriate use of citations. Yeah. There is nothing wrong with finding a wonderful tutorial that explains how to get a simulation to run. In my experience, most of these tutorials do not go through the additional step of testing our hypothesis. Okay? Usually they get them to run a couple of times, and yes, maybe they can show a few changes in parameters and what you would expect. Nonetheless, usually they're kind of one-offs. That's it. Okay? Either way, even if you find a wonderful tutorial that explains how to do exactly what you're trying to do, please cite it appropriately, okay? This point is something that for ABET we've been tracking, is the appropriate use of acquiring prior knowledge that's out there, learning, and we've connected some of these different outcomes to how well are we doing with the citations. Okay? We've talked about using Zotero. If you've forgotten how to use Zotero, feel free to come to office hours. Just, that is going to be a point that is easy to get right for the final grade and on the rubric. Last time I taught, though, people didn't pay that much attention to it, and so as a class, collectively, our meeting that criteria was not as high as I would like. Okay, so please cite your references. And we've discussed the policy and the syllabus for the use of generative AI. And just like to emphasize again, the idea is that if it's something that is not general knowledge, 1 + 1 = 2, let's get some citations in there. Okay. Any questions on these aspects of the final project? Convergence, citations, what's coming up? Again, we're not going to have final presentations live, so that I expect to come in a 2-minute live recording, or 2-minute recording that is somehow similar to a lecture format, in addition to the 2-minute format. Any other questions on these aspects? Please feel free to stop by during office hours. It's nice to connect, in some cases, faces to names that I see. Okay. All right, so let's get on to today's topic. We're going to have a review on buckling and fatigue. We should be able to get through these topics with demonstrations, provided that I do what I'm supposed to do and ANSYS does what it's supposed to do. And these topics are stepping stones toward vibration, which is what you'll get to do with the video tutorial. Okay? And maybe some of you have already completed it. It's kind of, I think it's a little bit fun, it's a little bit interesting. Okay? And the idea of modal analysis is directly applicable to what we'll talk about in buckling. It's actually kind of similar in terms of what the solutions look like. Okay, so buckling. In our last meeting together, we discussed this bar under tension, and maybe it's not quite a bar. Maybe it's more like a flat plate. It's kind of thinnish. Okay, so maybe bar is not exactly the best term. Nonetheless, we don't really care about buckling when we have a structure under tension, at least one of these primary structures under tension. Think for a minute, when have you encountered a physical system that buckles? So what are some systems where you might want to consider buckling? Watching two. Alex? Not now? No? Okay. John? No? Anyone else? Okay, yes. Anthony. Your knees, okay? Yeah, so buckling on your knees, that's true, right? Hopefully this way, right? Instead of that way, right? Yes, okay. And what's the idea there? How's that similar to like the types of buckling that we're thinking about in our physical simulations?
Basically under a certain load, your knee is the only point of movement.
Okay.
So if you overload your straight leg, you're overloading the amount of stress that your bones can take, so it has to be compressed.
Okay, interesting. So overloading the amount of stress your bones can take. Let's analyze that for a second. Is it really the stress that the bones can take? Because we do think of a critical stress, yes. Okay, right. So some cases we do, we'll talk about this in the Johnson case, we do consider the stress of the material. Okay? In Euler buckling, where it's very thin and slender, do you remember, do we consider, and it's kind of right there, do you see the yield strength of the material involved? No. So this is kind of like an elastic, it's AN space, elastic, not inelastic, and elastic, instability, IN, okay? So what's really happening is the knee, okay, so like really the buckling, right, let's say that I've got my leg right here, it's a nice, beautiful leg, okay, and I'm putting a compressive load, right? And if I were to, do some squats or something, as I'm applying that compressive load, any perturbation, right? Any kind of off-axis perturbation, so it's not quite loaded perfectly here. Anything that's like lateral in terms of the force that's being applied, that will essentially lead to some type of spontaneous, or some type of instability that's going to want to cause my leg to go out. Okay, in a direction where the force is not really being applied. But if this is my leg, and now I think of all my tendons and everything as strings, and I'm in some type of tensile testing machine that's pulling me apart, right? It's not going to be able to. It's not going to buckle, right? It's just going to be something that's pulling. And that in that case, failure is going to be due to the strength of the materials that are involved. Okay? In this case, you might have a very strong material, but because of the geometry, you have buckling. Now, as engineers, why do we care about buckling? Yes.
Failure.
Yeah, so it's a type of failure, correct? Right? There's a lot of systems that we design where there's compressive stresses involved, and so what we might need to do, even though we might be below the thresholds of the stresses that we're calculating, we may need to make sure that, or we may need to essentially widen the cross-sectional area, increase the cross-sectional area, so that we avoid the possibility of buckling as failure. Buckling can happen in devices as well. What are those little things? The pockets? What are they called? You remember they're like the little suction cup things that you flip back and forth, right? That's an example of an elastic instability, right? You pop it one direction, whoop, you pop it another direction, whoop, right? And it stays there. Okay, that's another example of buckling. Okay. So it's, in that case, right, it's actually somewhat of a useful mechanism, all right? It provides some type of enjoyment. You can think of buckling not just kind of in poles and columns like the Romans were thinking, okay, but also in terms of sheets and planes. Okay? So you can imagine that if you actually on a sail, for example, it almost with the battens and everything, you can also see that a sail, once it's got air coming into it, it will pop into a particular configuration, right? And then when the wind comes in another direction, it flips it to the other side, okay, with the battens. So there are some useful aspects of buckling, but typically we do try to. Okay. Now, what do you remember? I mean, there are a bunch of equations, a bunch of things here. What were some of the guidelines? What were the things that you remember when you talk about Euler and Johnson for buckling? Do you remember the general idea. When was Euler buckling applicable? When was the Johnson parabola in use? Is this familiar? Sound familiar? Yes, Anthony?
Euler was for long, slender feet.
Right. Okay, so Euler criterion is valid, like you said, where you have a high slenderness ratio. Okay, and what is the slenderness ratio? Well, the slenderness ratio is this term over here. Oh, let me get it. This is what we consider to be the slenderness ratio. Okay. And the name kind of speaks to what it represents. If you keep the cross-section the same in its area and you increase the length of the object, that would be increasing the slenderness ratio. And it's this rho term is what we call the radius of gyration, and that is going to be equal to the square root of the second moment of area, that I, over the area cross-section, areal cross-section. Okay, and anyone remember the second moment of area for rectangular cross-sections? Yes, Rishi?
Is it 1 over 12 PHQ?
Yeah. All right. So I, right, this is a second moment of area. For rectangular cross sections, we said it was, and this is assuming that this is the B, I'm sorry, that's the H, and this is the B, okay? So in this scenario, okay, like now look at the picture, right? The H has a bigger effect, right, in terms of resisting the buckling, okay? And so you can kind of see if I have this thin sheet, right? And let's imagine that this is that thin sheet, right? So it's going a lot in this direction and it's going a little bit in this direction, right? You gotta sense that it's going to buckle, right, in these directions, right? It's not going to buckle. It can. That is a mode of buckling. We can talk about that, and you'll see it more in the vibration analysis that you get to do for the homework. But that's going to be much less probable, much less likely than buckling in the direction of thickness. Okay? But that H is what determines that. So if you're like, oh, how's it going to buckle in the orthogonal direction, right? Then you have to calculate those stresses. You have to flip the B and H. Now, for a circular cross section, for circle, anyone remember what that equation is? Yes? Okay, so it's going to be, like you said, c to the fourth pi over 4, right? So that was, remember we used J, which is the polar moment of area. That one is pi r to the fourth over 2. And I is alphabetically comes before J, so it's less. Great. Okay, so now let's do a little bit more here in terms of maybe the actuals of buckling. So this is kind of a classic Euler beam buckling idea, and this is P critical, and this was on the previous slide. And as we said before, it's dependent on the elastic modulus. It's dependent on the moment of area, second moment of area, and it's also dependent on an effective. Now, another way we sometimes write this out is in terms of a critical stress. So even though Euler's beam buckling does not depend on the yield strength of the material, we can still associate a critical stress with this behavior. Okay, so we take the critical force that's being applied compressively, divide by the cross-sectional area, and that's the critical stress. And if you plot this out in terms of the critical stress over the elastic modulus for the y, so this versus the slenderness ratio, you get a line on a log-log plot that looks something like this. What is the slope of this line? In terms of decades versus decades. Yes? You're saying it. I saw you mouth it. It's -2, right? It's -2, right? So you could look at it this way. There's the coefficient, right? -2, right? Or you can look at it as, all right, I go down 2 decades for every 1 decade. All right, so this is 1, this is -2. Okay, and that's how you read this out, right? It's got the slenderness ratio, right, to the -2 power. So when you put this on the log-log plot, you're taking a log of both sides. This is the behavior we get. You know, and I've said this joke probably too many times before, but if you get data and you don't know what to do with it, and you want to try to get a straight line, just plot it on a log-log plot and see what happens. Right? A lot of data ends up looking like a line on a log-log plot. Okay, now the Johnson parabola says if you're okay, so we're looking at pretty long or pretty high slenderness ratios on a lot of cases, but 10 is a low slenderness ratio. And 10 as a slenderness ratio might actually not obey the Euler buckling behavior. Okay? And this kind of, you have an intuition that at some point buckling is not going to be a problem. For example, if I'm squishing a pancake, that pancake is not buckling. Right? That is just going to be dependent on the yield strength of the material, which is fine, right? That's what we studied in mechanics of materials. At least here. Other places they do get to buckling. Maybe this semester Professor Wynn will get to buckling. I'm not sure. Normally we wait to the DMC to talk about buckling here. But anyway, so there becomes kind of this hybrid idea, right? It's not too slender, it's not too wide, okay? It's kind of in between. And so the Johnson parabola is what helps us describe these behaviors that are kind of in the in-between category, right? Now, here, this is what we'll call kind of the tangent. These are coordinates. Okay, when you're looking at the critical, so you're going to look at the critical stress, okay, and you're going to look at the slenderness ratio. Okay, so we have these two axes, and the Johnson parabola kind of does like what you think. It does a parabola thing. Okay, and these values right here, we'll call this the critical one. Or we'll call them the tangent values. Okay, the tangent point. These tangent points represent the transition from Johnson buckling to Euler. So Euler is going to, the red that you see, this is the Johnson parabola. Okay, but the Euler, okay, is going to look something like this. So this is Euler, and this is, the red is the Johnson. Okay. Where do I trust what? Where do I trust these lines? Yes, Anthony.
For the point,
Yeah.
it's Johnson, that's a low slenderness ratio, and afterwards it's Euler.
Exactly, right? So you don't trust Johnson once it gets into that regime, okay? And we don't trust Euler before it gets to that tangent point. Okay, so there's this tangent point, and it's interesting that the slenderness ratio has a slightly complex, right? The square root of quantity 2 pi squared e over sy, right? So it has that whole value together. Okay. That's the slenderness ratio, right? That's what this point is, right? This is going to be the tangent point. Right? So tangent point with slenderness ratio of square root of 2 pi squared e over sy. And then in terms of the critical stress, it's at half. It's at half of the value of the yield strength of the material. Okay. I plotted this in MATLAB a couple days ago. All right. So just to kind of make sure that things work out, and also to show the trade-off, right? So below this, let's say the tangent point, the yield strength is 500 megapascals for the material, so around 250. All right, so this is probably around 250. Okay, that's the tangent point. Okay, and this is ignored. And then once you get over here, this part is ignored. Okay. Now, what we can do in ANSYS is put in a static structural problem and then have it calculate buckling properties. And I'll show us the modes. And it should essentially be able to help us understand and relate to this entire behavior. Okay. Maybe we'll just go ahead and we'll go to ANSYS and we'll come back to this. Yeah, we'll come back to this in a second. All right, so let's do a couple of things here. We'll get Workbench going. And we'll also get MATLAB going. And we'll see which one moves first and how badly this crashes my computer. So when we do our MATLAB analysis, MATLAB would just be, okay, equations for the Euler and the Johnson parameters, right? And let's take a look. We'll do a simple geometry that allows us to kind of make some comparisons and see, okay, where are we on the slenderness ratio regime, and what do we expect to have as a result? Okay. So Workbench is up and MATLAB is up. Okay. And the geometry that we're interested in executing is back here. So we have a wall with a plate coming out of it, and we're going to say that this plate is 150 millimeters long. It has a span of 3 centimeters and it has a thickness of, I think it's 5 millimeters. 0.5 centimeters. Okay, so if we think of this now as a system that's, you know, let's just turn it this way and we're compressing it. Okay. There's a force, it's going to be, I think, 10,000 kilonewtons, or 10,000 newtons, 10 kilonewtons, that's a lot, okay, coming down on it, and we're going to expect it to kind of bow out in kind of this direction. The boundary conditions, what do they kind of look like? Well, it's essentially locked into the bottom, right? It's a cantilevered beam, so it's fixed at this end, but on this end I have some choices to make. Okay. If I have it kind of just like free and hanging out here, okay, I'm going to say, and I'm applying the force. Right, I'm just going to kind of say this is like a free end, but I have a force being applied. Okay, and if that's my situation, I might take a look at this type of chart. Okay, we talked about slenderness ratio as being some equivalent length over the radius of gyration. Which one of these scenarios describes what I just? Well, which one of these scenarios applies to the scenario I just described? Fixed on one end, force and compression, but like free-ish. Okay, at least in 2D. Let's say in this direction. Which one of these do you think applies to this situation? The fifth. 1, 2, 3, 4, 5. Okay, you could have said second from the right, but sure, sounds good. All right. Yes, second from the right. Okay. This one is free-ish on that one end. Okay, so it can translate and it can rotate. While the bottom is glued to the bottom, okay, or the bottom of the beam is glued to this structure at the bottom. Okay, so that means that the theoretical value, for the equivalent length would be twice, two times the length. Okay, would give us the equivalent length theoretically, and then they recommend, for design perspective, to use 2.1 in this case. And in most cases, they augment this a little bit, except for this case and this case. All right. So this is kind of to give us some idea of what the equivalent length is. Then we can calculate the slenderness ratio. We can have an idea which domain we're in. Okay. So we're first going to in ANSYS, we're first going to do that simulation. Okay. But before we do that, you can see here, now you're like, oh, I don't like reading code, all right? I have an elastic modulus of 200 gigapascals, yield strength of 100 megapascals. Here's the length that we talked about, the 15 centimeters or 150 millimeters. The span of 3 centimeters or 30 millimeters. And the thickness, the height, the thickness, let's say, of the plate of 5 millimeters. And then I have my I have my A, and I have my radius of gyration, and then when I got to the equivalent length, look, I put in a 2 there, okay? This 2, or the 2 times L, right, is going to give me an equivalent length that I can then use to calculate the slenderness ratio and the critical stress and the critical force, right? So we run this, and what do we see? All right, if we're using this system, okay, the critical force there is going to be 6,850 newtons, and the critical stress, according to Euler, is going to be about 46 megapascals. Notice that is much less, right, than the 100 megapascals that we have in this situation. All right, for the material, and then the tangent point, okay, is going to have a slenderness ratio of about 200, all right? So if your slenderness ratio is above 200, which it is, the slenderness ratio that we calculate in this case is 207, then you're good with Euler. So all this is good. All right. If you're below, okay, if you were to be below, then you could use the Johnson. All right. So this is kind of garbage right now, but the stuff above Johnson is valid because our slenderness ratio for this situation is higher than the critical or the tangent point slenderness ratio. All right, so let's see if we can do this at ANSYS and let's see what we get. So to get started, we're going to do a static structural analysis, and we can go ahead and click on the engineering data, and we'll go ahead and we'll add our generic steel again, and here we'll give it a density, and we'll call it 7850. We'll also give it isotropic elasticity. So that means that we have a Young's modulus of 200 E9, that would be 200 gigapascals. And 200 E9, yes, right. That's, or 2 times 10 to the 11th pascals. Okay, and the Poisson ratio of 0.3 is fine. And we'll leave it here, okay, for now. Let's go ahead and go back to the project. Geometry, yay, we get to do 3D. And we're going to go into space claim. I did right click. I thought I right clicked. I'll right click again. Okay, and we're going to enter the space claim. We're going to try. And so we have our kind of simplish geometry, which we've done before. It's not a bad idea to also make sure your units are right once you get into space claim. Mine is going to open into millimeters, which is just fine. When we did things in the micron scale previously, right, it was a good idea to go in the options and change that. In the geometry, we won't be specifying the boundary conditions. That will happen when we bring it into the mechanical model. Okay. And we're still waiting very patiently. So we're not going to draw it with a length, you know, an equivalent length. We're going to draw it to the length that we have in our simulation or in our defined problem. Okay. Still starting. Still thinking. Okay, looks like there we go. Okay, so we have some kind of warning. Click, well, I guess I'll click here and then click here. That's going to be the surface we select. We click on the rectangle one time. We click once at the origin. We move this over here. No hands. Then 150 millimeters. Hit tab. No hands still. Then 30 millimeters. No hands. Hit enter. Okay. And voila, that's our top-down perspective. We click on the enable. Sketch editing. Pool is already selected, but that's what we need. We can maybe move this just a little bit, and then we can come over here to the arrow. We hold down the left button, we pull, and then we hit 5 and enter, and then it's at 5 millimeters. We can just come over to the upper right and close it. Then we'll open up the model. Click. And the first thing before so you'll see that there's this eigenvalue buckling. That's what we're going to use in a little bit. But first we're just going to put the load in compression. Until we enable the buckling, ANSYS doesn't care about the possibility of buckling. It's just going to calculate the stress through the structure. So we're waiting and Should have enough battery power. Any questions up to this point in terms of what we're doing? Any insights that you'd like to share? You're like, well, we already got the Euler and the Johnson. Why even do the ANSYS? I just use Euler and Johnson. Well, not everything is a constant cross-sectional profile, right? So you can put in, we're doing a very simple case here. Nonetheless, if you have a more complicated geometry, a table or something else, right, you can do that and it will calculate for you where the hot spots for buckling might be. Okay? Yes?
How does ANSYS solve this problem?
Okay, so what it's doing, this right now is the finite element, straight up. Okay, I can talk about mechanics. What it's going to do instead is, when we get to buckling, it actually solves an eigenvalue problem. And this is what it does for vibration as well. So impressionist perspective, okay, but essentially it's going to be calculating out eigenvalues, right? That will give us these stresses, the magnitudes will give the values, the magnitudes of those magnitudes. The magnitude of the eigenvector will give you the magnitudes of the stresses associated with the buckling. And then the vectors will help us figure out what the mode looks like. Okay, so it's doing this all in the back, right? Impressionist perspective. So here we go. It's good to note that the geometry is only one solid. It's also good to note that I made a boo-boo, all right? I have two materials, but I did not make that generic steel assigned, okay? So you'll see that it's assigned to none of them, all right? So if we go to the solid and we come over here, you want to change it over to the generic steel. Okay, so now I know it's there. For the mesh, we're just going to use the element size. Okay, and here, we've done this before, but if I put in 5 millimeters, it's not fine enough, at least not for our liking. It looks good, and it actually would probably do just fine for a lot of this analysis that we're doing today, but we can, without much difficulty, refine it a little bit and put it to be smaller. So here we go. All right, and now, okay, what we're going to do is add a fixed constraint, a fixed support on this side. Okay, and we hit apply. Okay, and that should be good. And on this side, we're going to add a force. And we select this face like that. We're going to go ahead and put it in components, and it's going to be in the minus x, and this is going to be minus 10,000, okay, minus 10 kilonewtons, like that. For our solution, we can include the normal stresses. Okay, we can include deformation as well, okay, just like that, and we can go ahead and hit solve. Where is, right here, the force, of course. I have to hit apply. There we go. All right, let's go ahead and solve. And the value that we should get for this particular system is minus 67. Okay, minus 67 megapascals. Okay, that's just the force divided by the cross-sectional area, B and H. And it's going to be a Poisson effect, so it will be a little bit varied at the wall. Okay, but if we look at this value, let's say normal stress. Okay, why? It's just this. Okay, we want to do it on the whole thing. not just the face. All right, let's get rid of this. Okay, insert the normal stress, all bodies. Okay, and we should be able to retrieve this now. Okay, so there you go. All right, if I take a probe and I look at it somewhere around here, it's minus 67 megapascals. Very satisfying. Okay, now, because of the Poisson ratio, these values are a little bit higher, as we discussed. And what we'll now do, okay, is close this down, and we're going to add an eigenvalue buckling analysis. So we come over here to this eigenvalue buckling, and we can take the solution, pull it over the solution, and it brings it right in, and then we can double click on the model to run the buckling analysis. What are we trying to get out of this? Well, we're attempting to be able to see, okay, what were going to be the problematic what are the problematic loads, I guess I could say, and what is this kind of load? What's the kind of what load do we expect buckling to occur? Did I not double click on it? Okay, now it's going. Okay, double click on the solution. Or the setup. Okay, any of them either of them would have been fine. Okay, so now what we see is that in this tree, we have the eigenvalue buckling information there. And for solution, okay, we can go ahead and let's put in the deformation. Okay. And what's going to happen when we run this, and I misspoke previously, it's not so much about telling us, okay, where are the hot spots? It's more like, what is the hot spot, or what is the critical force across the entire geometry? And that force is going to be a factor, a load multiplier across the force that we applied. That was the minus 10 kilonewtons. Okay. So what we should see here are a buckling profile, which we could kind of expect, and a metric that tells us how much force, or what percentage of the force, or what multiplier of the force we need to get to that buckling. Okay. So look here. There's a mode like this. All right, you can kind of see it's curved a little bit, and that would be our first mode of buckling. That's what you kind of expect. Okay. And then, though, maybe what you don't expect is that there's also a higher mode. And this mode, it kind of has it bow out. Okay, so the first mode is kind of like, oh, it just shifts over. Like that nice drawing that we have, right? This drawing right here, the fifth one, all right? John said, right? Or the second one from the right. This one it's bowing to one side. That first mode is, at least. And then the second mode is not in that drawing, right? So the first mode, as we said, retrieve, right? That's kind of like what you saw in that drawing. And the second mode is a different in terms of it keeping it kind of over the top maybe, but it's punching it out slightly. Now, on the right, you see these load multipliers. we were multiplying, or we were applying a force of minus 10 kilonewtons. This load multiplier says if you take all the loads that you have on your system and you multiply it by 0.69, that's when you have buckling in the first load. If you multiply your system by 6.2, all the loads, that's when you would have buckling in the second. So in our case, the first mode, right, is going to be more critical. That's the lower force. So that suggests, right, minus 10 kilonewtons times 0.69 is minus 6.9 kilonewtons. What did we predict over here? We predicted 6.8. That's pretty good. Okay, take that. Okay. Now, this was a situation where we had the free end. What if we're interested in trying to constrain the system a little bit more? Let's say that we want to constrain the system so that, you know, maybe it could kind of rotate on that end, but we're going to keep it from translating on that end. Okay, because we're concerned about the buckling. Okay, so now you like build a whole frame essentially around this beam, okay, and you've got it so that it can rotate and it can translate downward, but it's not going to be able to translate this way or this way. Okay. Do you think the buckling force is going to go up? The critical buckling force? Yeah. Okay, and how does this chart help us? It tells us the equivalent column length goes down. It goes down to 0.7. So, we used a factor of 2 before. Now let's use a factor of 0.7. So we come into here and we say, all right, I'm not going to use 2, I'm going to use 0.7. Well, when we do that, what happens to the slenderness ratio? Well, the slenderness ratio goes down, right? It goes down to like 73. Now, the tangent point slenderness ratio hasn't changed. That is dependent on the material properties, okay? The elastic modulus and the yield strength of the material. Okay? So that tangent point is still close to 200. This means that if we want to do our buckling analysis analytically, if we want to do analytical buckling analysis using what we know here, we should probably be using Johnson. So what does Johnson say? Johnson says, okay, that the critical stress that we have involved is going to be 93.3 megapascals. And so we should probably, let's figure out what the Johnson okay, is going to be equal to the SCR Euler times A, okay? And sure, we can make it all beautiful if we want. I probably should have copied the other one. That would have been nicer. Okay, but it knows. We'll just leave this in terms of, oops, sure. I have it for whatever. Okay, so we've run this out. Why did it not display the Johnson? Oh, because I interrupted it. Okay, I put it up higher. Okay, so there it is. It should be about 5.6 That's annoying. I'm just going to move that down. Okay, because I. Okay. There. All right, so it should be about 5, or it should be 56 kilonewtons, or 56 kilonewtons. Okay. All right, so let's see. How do we go about changing that in ANSYS? What do you think? I don't want it to be able to. I don't want to be able to translate at the top. So what do we do? I can still have rotation, but I want to change it so it doesn't translate at the top. What do you suggest? Yes, Anthony.
Displacement constraint.
Yes, in which directions? So you can use, we have a coordinate system here, right?
So C and
Correct, that's right, okay? So we'll come over here, and now for that where we had the force, that same face, so we'll add a displacement constraint, and we'll apply it here. Hit apply. X is still free, but for the y, okay, so we'll say yeah, that's and the z, okay, those are going to be fixed. Okay, so now we can go ahead and we can solve this entire problem. And what we're going to be looking at is the load multiplier. See, the load multiplier reflects, or it reflects this change in the boundary conditions. And what we should see, right, is that instead of it buckling, that load multiplier for mode 1, instead of it being less than 1, it should now be more than 1, right? Because we're applying 10 kilonewtons, and we're hoping that our analysis is correct, and it will be closer to 59. All right, so we come over here. Oh, we had to run this too. Solve this. Okay, and let's look at a solution. Look at this. For mode 1, okay, we get, what? So I just wanted to create, okay, this is why. Okay, here we go. Now, retrieve. Look at this. This is mode 1. It looks pretty close to what we would expect on that picture over here. See, it looks kind of like that. And interestingly, what does it tell us? It tells us that the load multiplier is now 56 kilonewtons, right? 56 kilonewtons versus 56 kilonewtons. Now, did ANSYS care whether it was a Johnson or a Euler buckling problem? No, it did not, right? It's solving this eigenvalue problem, which is taking into account the fact that the slenderness ratio has gone down. Okay? And so this is a kind of a very nice, useful tool, especially when you have more complicated geometries. So now we've done buckling. We're now going to change gears and talk about fatigue. Yes, Rohan.
What is the other eigenvalue represent?
What?
What is the other eigenvalue represent?
The other,
Like the other eigenvalue that it's
like the other mode that it came up with? That represents another potential bowing of with a different configuration. that does in fact would buckle, all right, critically, but you'll never get there. At least, right, because that load multiplier that load multiplier is 16. Okay. So it can exist if you didn't fail, right? It's solving a mathematical problem, but it's not necessarily a realistic situation, right? You're going to fail before you get to this other mode. But in vibration, it's doing a similar solution solving. We do get to those other modes. The multiple modes are very important, okay? And you'll see that in the assignment. Okay, so I'm running behind, which is okay. Fatigue. Here at Rutgers, that's NDMC. What are some of the salient attributes of fatigue that may or may not be there, that you remember? What were the things that struck your fancy when you studied fatigue? Anyone in quadrant 4? Fatigue. Yes.
Cracks and failures.
Yeah, so cracks and failures, you want to be a little more specific?
I don't know, like after a certain class, like some people fail.
Okay, and how does cracking lead to failure?
Once a crack is like large enough that like shatters.
Yeah, okay, it could. It probably won't shatter because it's usually from more ductile materials. Okay, if you have fatigue, all right, the crack is opening and closing and it's propagating, and the effective cross-sectional area that has to carry all that load gets below essentially a static level of width or area that gets to a high level of stress, and then it will essentially statically fail. Okay, so that's right. So there's this new connection between these micro cracks that can form and lead to failure. We talked about, well, I don't know if we talked about it much here, but there are issues with pressure vessels as well, and in particular fuselages of airplanes. As they get pressurized during takeoff, okay, and that puts the outside pressure goes down, and so the internal pressure inside, the relative pressure right between the two, goes up, and that leads to tension when it's high in the air, and it comes back down. Right? When it comes back down, then that pressure is released, right, and it relaxes a little bit. So that's a case where takeoff and landing essentially cyclically load this fuselage that undergoes fatigue. On the material side, you remember the endurance limit? Hopefully, maybe, kind of, the SN, okay? What is, or SN prime, okay? If you have kind of the prototypical RR test, what is nice about the endurance limit? What does the endurance limit tell you in terms of whether or not you will fail and your steel material? Yes, Anthony.
Alternating stress is below the current endurance limit, no matter how many cycles you do.
That's right. So typically we're trying to make sure that our alternating stresses, the magnitude of it for the RR more case, are below this limit. And if they are, everything is awesome. Okay? And you did good midlines and all that kind of stuff, right? And you're looking at, okay, if it's not plus or minus the same value, all those types of scenarios, right? You could also calculate what the effective loading stress was. So if you end up above the endurance limit, so in this case, if you're above 30 KSI, that's when you have to be concerned. And that's when you can start to erode and eat into the life of the material. So we're a little bit running low on time, but you can go through these slides. You have them. You can watch the other class too if you like. We're going to essentially change this problem into a beam bending problem. Okay, so we're going to have now a transverse force being applied up and down, and it's going to be 300 newtons. How do we do this quickly? Well, we hope that we can duplicate this system. Which should bring in another box for us. And we're not going to use the eigenvalue buckling. We're going to go back to the structural system, and we're going to use a tool that allows us to calculate life. All right? And so that is coming up. But in order to do that, I actually have to manipulate the material. So here, there's this material property life, and you can put in values for the SN curve. Okay? And in this case, what we're going to use is the 0.9 times the ultimate tensile strength. Okay? So if the ultimate tensile strength is 500 megapascals, 0.9 would be 450 megapascals. And then the SN prime, the SN prime value with all these 1 is equal to the SN, the endurance limit there. That is going to be half of the ultimate tensile strength, and so that's going to be 250 megapascals. So you can actually put these two coordinates into ANSYS so that it then knows something about life. So at 1,000 cycles, we're going to say that this is going to be 450 e to the 6, or E6 times 10 to the 6. And at 1,000,000 cycles, this is going to be 250 e to the E6. All right. So this represents the knee, right? And this is the portion with a slope, and then it goes flat there because that's where you have infinite life. Okay, so now we've manipulated the properties, and we've got the model, which I'm going to close because I don't think it updated with these materials. Maybe it did, actually. Okay, but now I'm going to double-click there just to be safe. I'm going to open it again now that I've updated the material properties. And if we look while this is opening, we can predict the number of cycles. Well, first off, where is this thing going to be failing? Where do you expect this thing to fail? In this case, unlike the buckling problem, okay, we can have an idea of where we're going to have a problematic situation. If I'm bending this beam like this, where do I expect the failure to occur? Yes? Yeah, the top or the bottom face of the wall, right? Because this is going back and forth. So, this will be in tension when this is in compression. This will be in tension when this is in compression, right? It's going back and forth. Okay, and so if you do the calculation out, what you'll see is that the life of this system, okay, and this is not assuming there's no stress concentration really involved here, right? And ANSYS is going to be having us. Can be having that stress concentration, all right? So like if we think a little bit away from the critical hotspots, we expect that this thing should last about 14,000 cycles, okay? So let's go ahead and do it real quickly, or try to do it quickly. In this case, we're going to change the direction of the force, okay? Remember, it used to be minus 10 kilonewtons in the x direction. Now we're going to apply that force, or apply any force in the z direction, and we'll say that it's 300 newtons. Okay. Under the solution, we can insert a fatigue tool, just like this. Okay? And this tool has various things that you can do. We're going to be doing fully reversed, right? So we're oscillating plus or minus 1 times the amplitude of the load, okay? And we're going to insert a life, okay, like that. So we're going to see something about what the life is like, all right? So let's go ahead and solve this new problem, or this modified problem. And you see, it's not really solving anything new, okay? Unlike the eigenvalue buckling problem, okay? It had to run some new calculations. I mean, it's doing some calculations, yes, but really what it's doing here is just should be what just happened. What just happened? I'll delete this. I don't think this should be the problem though. Okay, that's good. That's not good. The stress should not, deformation, these are not right. Force, geometry, face. Ah, what's the problem? What was the problem? What did I do wrong? Yes? Yeah, I left the constraint on at the end, right? So let's suppress that. That was the translation constraint. So of course it's going to be 0. Okay, so let's solve now. I just had a force essentially slamming against the wall. Okay, and then it did nothing. Okay, so now, yes, that looks more like what we're expecting. Okay, and we'll go ahead and, so you see here, like just looking at this normal stress, it is, maybe it's getting up to like over 300, 400 megapascals, right? So we see that we're above the endurance limit. The endurance limit was 250 megapascals, right? And there are areas of this structure that are going above that. So now, when we add the tool, okay, and we look at the life, we can retrieve this result. I guess we have to evaluate it. Oh, it's okay. So you saw that? It doesn't say there's a. Come on, why is it? It's not. I thought it would have been. Okay, so let's close this. It's because it's not accessing the SN curve that's in Workbench that I thought we put in. Okay. So we go back to Workbench and we make sure that the engineering data, okay, it's in there now. Okay, we have this SN curve. I'll go ahead and yes, I'll default the solid material for the model. Okay, and we'll go back to the project. We'll update the project because it's probably like, oh, you made that mistake, you haven't updated the project. And this can take a while. Okay. And it failed. So this is why I probably have to, just like you have to do in your homeworks, I probably have to go and delete the static structural, okay? And after I added the material property, then do the duplication, okay, of that, because it's probably going to give me the same error. Let's see. Over error. Okay, it says inside because invalid or missing stress life curve. Okay, so I apologize, but I'm pretty sure that's what the issue is here. So I have to delete this. And we have to then duplicate this. And we have to go ahead and redo all those loads. Okay. So we get rid of this displacement, we change the force, we go ahead and we can solve it. Normal stress looks good. We add the fatigue tool. We calculate the life. We evaluate these results, and voila. Okay. All right, and then we put the probe on it. Okay. So you see out here, this is infinite life plan. Here, as we get closer to the wall, it goes up. All right, and here in this kind of area, or I mean, it goes down actually. The life, right? The number of cycles goes down, right? And then as we get into the wall, we're looking at like 57,000, right? In this critical area, it's like 17,000, okay? And fatigue, as you can see, you go just a little bit away, and the number of cycles changes by an order of magnitude. This is reflective of the slope of the SN curve as well. So when you're designing your system, you have to be very careful, okay? If you want to design for low cycle fatigue, you got to know what you're doing, all right? And you have to be very conservative with your inspection and testing, or you do what a wise engineer would probably do in most cases, and you design to be lower than your endurance limit, okay? So today what we've covered is a bit on buckling and fatigue, and it's a stepping stone toward studying vibration. I'll bring up the attendance real quick in a minute, but we have someone who would like to talk to us for a minute about an upcoming activity. I'll go ahead and actually I'll shut off the recording so you don't have to be there for that.